All right, man. Logarithms test review. Let's get right into it. So, number one, the asymptote of the graph. So, here, the thing that you need to know is that, all right, exponentials have horizontal asymptotes and logarithms have vertical asymptotes. So, this is definitely an exponential, mainly because the variable is in the exponent. So here, the asymptote is going to be at x equals 0 in an exponential function. Now, if there's a vertical shift, then that's going to move. And here we see that there is a vertical shift. It moves up 5. So x equals 0 is the horizontal asymptote, and it's going to move up 5 places. So x equals 5 is the horizontal asymptote. Number 2, identify the decay factor in the model. So the decay factor is this value right here, 0.89. So that's the decay factor. Now, the percent that it is decreasing is 11%. So see if you can convince yourself of why it's 11%. Right? You have to compare it to 1. How much is 0.89 less than 1? And it's 0.11 less than 1. Right? 1 minus 0.11. So 1 minus 0.11 is 0.89. Therefore, the decay factor is 0.89, but the percent is going to be 11%. All right, number 3. Explain the meaning of log base b with argument y. What this means is that there's some number, which we call the base, and it's going to be raised to some exponent, and it's going to equal the argument y. So the part you're missing is that it has to be equal to something. Right? You set it equal to something, then you can convert it. So this is really the whole main point of logarithms, is that you can rewrite it as an exponential and then do something with it, basically. A logarithm, all right, number 4, logarithm with base e is called a natural logarithm. Natural. All right, number 5, is it an exponential or polynomial? So it's definitely an exponential, and it's because x is in the exponent. All right, 6 through 9. 6 through 9 are easy. You're just converting this log into exponential form, right? Exponential form. So it's always the base raised to what's out here equals the exponent, or equals the argument. Equals the argument. So 7 to the second power equals 49. Number 7. 4 raised to negative 1 equals 1/4. Right, all we're doing is converting logs to exponential form, meaning the log goes away and we have a base that's raised to an exponent. Number 8, 16 to the 1/2 power equals 4. Number 9, 3 raised to the negative 2 power equals 1/9. Okay. Number 10. So here, we're simplifying / evaluating without using a calculator, meaning that each of these logs, 1 through 25, they equal something. Right? They equal a number. These are pretty I would say, simple ones because they can be reduced or simplified rather. And it's going to equal something. Now, you just choose a variable, right? There's 26 letters to choose from. Typically, we like to choose X. Now, in the event that X is already taken, then we'll choose something else. Okay. So the idea is going to be to rewrite the log as an exponential. That's the most simplest way. Just rewrite it as an exponential and then change one of the bases so that they have the same bases. Then you let the exponents equal each other. That's one method. That's like the most basic method. There are other properties that you can utilize if you know them. So I'll go through the first one with you. So 3 raised to x equals 243. Okay, so here you're going to have to kind of figure out 3 times how many times 3 to some power is 243. So 3 times 3 is 9, times 3 is 27, times 3 is 81, times 3 is 243. So 3 to the 5th power. 243 can be rewritten as 3 to the 5th power. So we've rewrote the log as exponential. Then we turned the 243 into a base 3 situation, right? The base is 3 with power 5. That's what 243 is. And now that the left-hand side and the right-hand side have the same base, we set the exponents equal to each other. And here we see that x is equal to 5. Another idea, right? Another idea is that if you could maybe rewrite the argument with whatever the base is first. So then this would be log base 3 to the 5th, right? Instead of 243, you rewrite the number first using the base. And here we have 2 nice properties. So first off, the exponent can come down in front. And then when the argument and the base match, that's just 1. Right? That's 1. So all this will basically be 1. And you just get 5 times 1, which is 5. So those are the 2 most common ways. The first one is by far the most basic way. And then as your understanding of logs develop, then the second way is probably a little bit more efficient. Just rewrite the argument, bring the power down, and then cancel the logs out. Number 11 is a log property, right? Anytime the argument is 1, I don't care what the base is, this thing is 0. Log base 1 or log base anything of 1, the argument 1 is always 0. So log 1 is 0. All right, from here, these should move fairly quickly. 1/6 to some power equals 216. So here, clear the fraction, right? Fractions are just not fun to work with. So you can always rewrite a fraction with the negative exponent. All right, so now that the fraction's gone, we make them have the same base. I'm gonna use 6. I can turn 216 into 6 before I can turn 6 into 216. If you get what I'm saying. So, right, I have to pick a base, either 6 or 216. I'm going to choose 6, right? Because 216 can be rewritten as So 6 times 6 is 36. 36 times 6 is 216. So here, the bases match. So I can set the exponents equal to each other. X is equal to -3. So number 13, 125 to some power is equal to 1/5. Again, step 1, clear the fraction. Rewrite the fraction. 5 to the -1. All right, then I'm going to choose 5. I can rewrite 125 as 5 to the third power. 5 times 5 is 25, times 5 is 125. So this is going to be 5 to the third power, but then times x. Right? When I have a power raised to a power, you multiply the powers. So it's 5 cubed to the x power, so 3 times x. So now that I have the same base, this is going to be 3x is equal to -1. Solving for x is equal to -1/3. Okay, number 14. So here, 3 to some power equals 1/3. On the right-hand side, we can clear the fraction. 3 to the -1, right? Because I can always rewrite a fraction using a negative exponent. Now that the bases match, I can set the exponents equal to each other. X equals -1. You could have done log base 3, 3 to the -1, right? Just rewrite it initially. The -1 comes down, so -1's in front. And now that you have a log and the base and the argument match, all this is just 1. So -1 times 1 gives you -1. So that's how you do that. Number 15. So 4 raised to x equals 2. So 4 to some power equals 2. We can rewrite 4 as 2 squared to the x power. So 2x, right? That's the exponent, 2x. And it's implied that there's a 1 here. So 2x is equal to 1, which means x is equal to 1/2. And that makes sense because 1/2 is just the square root. So the square root of 4 is 2. Number 16. 27 to some power equals 3. We can rewrite 27 as base 3. So base 3, 3 times 3 is 9, times 3 is 27, so 3 cubed. Multiply by x, the exponent. Okay, so now that the bases match, 3x is equal to 1. Solving for x is equal to 1/3. All right, number 17. So it looks crazy, but let's just stick to the script. So 4 raised to some power equals 4 to the 2/3 power. So 4 to some power is equal to 4 to the 2/3 power. The bases already match, so x is equal to 2/3. How many of you saw that you could bring the power down front and the argument and the base match and it's just 2/3? That's the level that we want to be playing at. Like right here, prime example. Right, like here I see that the base and the argument match. So the power comes down front because that's the property of logs. And then log base 27 of 27, all this is just 1. So x times 1 is just x. So all this is going to equal basically x. So that's what I'm saying. If, let's say you didn't see that, right? I'm going to let this equal something. I'm not going to choose x because x is already taken, right? X is already in the exponent. So I'm going to choose y. If we do 27 raised to y equals 27x. The bases match, and we set the exponents equal to each other. Y, the thing that I set it equal to, it's equal to x. So that means this log is equal to x. That's the bottom line. All right, 19. Again, we can use our log properties. Bring the power down front. And anytime ln and e meet up, it's just 1. Right? That anytime ln and e touch, they cancel each other out. So this is like saying 3 times 1, which is basically 3. Number 20, the same thing. I'm going to set it equal to something. So 4 raised to y equals this. 4 to the y power, 64 to the x power. All right, then I'm going to make them have the same base. I'm going to choose 4. So 4 times 4 is 16, times 4 is 64. So 4y, 4 cubed x. Now that the bases match, we can set the exponents equal to each other. So y, the thing I set it equal to originally, it's equal to 3x. So 3x. All right, so here's a new one. Number 21. So here, it's definitely a log. However, the log is in the exponent. This is going to be the base. Obviously, this is going to be the power. And then this out here is going to be the argument. So log base 10 the argument, this is going to be equal to whatever the power is. In this case, log 14. So notice that it is log 14, and what's the base? It's nothing written, so it's implied that it's 10. So here, the logs are the same on both sides, right? Like log base 10 of x on the left, log base 10, 14 on the right. So since I have log and a base 10, log and a base 10, the arguments must match. Like they must be equal to each other. We can equate the arguments to one another. So x is equal to 14. So you might have to go back and watch that one a couple times. All right, 22. So again, set this equal to something. 49 raised to x equals 343. Okay. 7. 7's the thing that I'm going to work with here. 343 should be a number that screams 7. Like the more you deal with 7, the more 343 comes up all the time, and then you start to realize what it is. So on the left, 49 is 7 squared, right? 7 times 7 is 49. And then to the x power, so you multiply 2 times x. All right, on the right, 7 times 7 is 49. 49 times 7 is going to be 343. So 7 cubed. Here, the bases match. So 2x is equal to 3. Solving for x. X is equal to 3 halves. All right, 23. 4 to some power is equal to 128. So 4 to some power is equal to 128. So 128 as a power of 4. So 4 times 4 is 16. 16 times 4 is 64. Times 4. Is that going to work? I don't think it is. No, it's not. No, that ain't going to work. Okay, so 2. I feel like 2 is going to work. So let's think about this for a moment. 2 times 2 is 4. Times 2 is 8. Times 2 is 16. Times 2, 32. Times 2 is 64. Times 2 is 128. So 2 to the 7th power is what that's saying. All right, on the left, I can write that as a base 2. So I tried 4. 4 didn't work. So 2 is the next best thing. So 2 squared. And now 2x is equal to 7 because they have the same bases. So x is equal to 7 halves. All right, 24. 24 is going to be similar to 21. Notice how the log is in the exponent. So this is good practice. Set it equal to something. So again, the base, the power, the argument. So log base 12, the argument's x, or the powers. So the power in the exponent is going to be written out here. So log 1264. So if you pause and think about that for a moment, log base 12, right, this is the base. This is going to be equal or raised to the thing that's out here, right? All this is the power. And then it's going to be equal to x. And that's exactly what we have. So on the right-hand side, on the right-hand side, 1/2, that's the exponent. right? Because the coefficient can be brought back up. Power can come down and the power can go back up. I'm bringing the power up because I want the logs to go away. So this is going to be log base 12 x log base 12 64 to the 1/2 power. Because I have log base 12, log base 12. Those, in a sense, cancel. Well, because they match, the arguments can be set equal to each other. That's, I guess, a better way of phrasing that. And 64 to the 1/2 power is basically the square root of 64, which we know is going to be equal to 8 or negative 8, right? Plus or minus 8. Plus or minus 8. 25. Set it equal to x. So 64 to the x power is equal to 16. 64 to the x power is equal to 16. So we want the bases to match. I'm going to use 4. Right-hand side, 4 squared. Left-hand side, 4 times 4 is 16 times 4 is 64. So 4 cubed. And then 3x is equal to 2. Solving for x. X is equal to 2/3. All right, number 26. We're going to expand these logs out. Okay. This is all multiplication. So I'm going to use addition. This is going to be opened up and we're going to use addition. So log base 8 of 3 plus log base 8 of x plus log base 8 of y. Right, because it's multiplication, you can open it up using addition. All right, 27. Same idea. The only difference is we have natural log, which is basically base e. So I'm not even worried about that, just natural log. So again, all three things are being multiplied. So this is natural log 10 plus natural log x cubed plus natural log y. The only other thing I see is that we always bring powers down in front. So final answer, natural log 10 plus 3 natural log x plus natural log y. All right, 28. We have division. So I'm going to open this up using subtraction. So it's always top minus bottom, right? Top minus bottom. So log 8 minus log y to the 4th power. I'm going to bring the power down because of log properties. So this is going to be log 8 minus 4 log y. Not bad. Just remember top minus bottom when you're using subtraction. Okay, 29. I'm going to do the subtraction first. Always start with division, in my opinion. So this is natural log 3y minus natural log x to the 5th power, but I know that's going to come down. So getting a little bit quicker. Okay, 3y can be expanded because it is multiplication. So natural log 3 plus natural log y minus 5 natural log x. That's it. Number 30. So we can rewrite the square root symbol as a exponent. So this is going to be log base 3 xy to the 1/2. Okay, instincts may tell you to bring the power down in front, which you can, but then that's going to have to distribute to everything. I'm going to apply it to the x and the y separately. So log base 3 x to the 1/2 times y to the 1/2. And then because it's multiplication, we can expand this using addition. So log base 3 x to the 1/2 plus log base 3 y to the 1/2. And then the last step, the powers can come down front, in front as the coefficient. So final answer, 1/2 log base 3x plus 1/2 log base 3y. Okay, 31. It's probably the most complex one yet. All right. I like to start again with subtraction. So this is going to be top minus bottom. So log base 3 27x squared minus log base 3 y z. Okay, so there's two things that have to happen on the left and then on the right of the minus sign. Right, on the left is going to be, this is multiplication. So this is going to be log base 3 27 plus log base 3 x squared, which that 2 can come down later, minus here, because it's minus two things that are going to be multiplied or added together rather, this negative is going to have to distribute. So what I'm saying is log base 3y. So it's plus because it's multiplication, right? This is multiplication right here. But it's minus because the negative is going to have to distribute. So minus log base 3 z. All right, so some powers can come down. So the 2 can come down front. And then, I mean, we're at the answer once the 2 comes down. If for some reason you're using some sort of solving software, PhotoLab, or whatever the hell it's called, PhotoMath, or an answer key, sometimes an equivalent answer is going to be to rewrite this argument as base 3. Right? Write it as a power and then bring the power down. I mean, they're equivalent answers. It's best to get in, I guess, the habit of it now. So once we get to calculus or pre-cal, dealing with logs, you're already used to it. So however you want to go about that. So plus 2 log base 3x minus log base 3y minus log base 3z. So I guess to show you what that would look like, 3 times 3 is 9 times 3 is 27. So 3 log base 3, 3. Right, because this would have been 3 cubed, and then the 3 comes down front. And then you notice that these match, the base and the argument match. So technically you could just say 1. But again, if you ask me, in my opinion, this is good, right? It's good. All right, 32. We're condensing. So it's already expanded and we're putting it back together. So first thing is to bring the powers up. So this is going to be log 7, 4 cubed plus log 7, 6. So 4 cubed, 4 times 4 is 16 times 4, 64. So this is 64. We can condense this one more time by multiplying the arguments. So taking 2 logs, turning it into 1 log, and then 64 times 6. $384. So log 7, 384. $33. Power can come up. So this is natural log 12 minus natural log x squared. Because it's minus, that means this part is going to go underneath. So natural log, so we take 2 logs and we're condensing them down into 1 log. So the argument is what goes down underneath. So this is going to be 12 over x squared. So we had 2 logs, natural logs, and then we condensed the arguments. And it's by taking the most right argument and then putting it under the left argument. All right. So here we have a couple different things. Well, there's 3. First off, natural log of x squared minus natural log of 3 plus the natural log of 6. So the way I think about it, when you have multiple things, multiple terms, do the term with the minus sign first, right? So because ln3, it's minus ln3, this argument is going to go underneath whatever's to its left. So what I'm saying is natural log x squared over 3 plus natural log 6. And now you can, now when you multiply the arguments, the 6 is going to be up top basically. So this is going to be natural log 6 x squared over 3, right? Because it's 6 times x squared. That's how you multiply fractions and a whole number. Well, 6 over 3 can be reduced to just 2. Natural log 2 x squared. And I'd leave it at that. Okay, 35. Power can come up for sure. Again, the power can come up. minus ln 8. I'm going to put the 8 underneath here. So this is going to be natural log of 3 squared, which is 9. So 2 to the 5th power. 2 times 2 is 4, times 2 is 8, times 2 is 16, times 2 is 32. Natural log 32 over 8, right? The 8 goes underneath it. 32 over 8, that's nice. That can be reduced as, what's that? 4? So natural log of 4 on top, right? It's the natural log of 4. So natural log of 9 plus the natural log of 4. And we multiply the arguments because it's addition. So natural log 36. 9 times 4 is 36. Okay. So the first thing I see is we have a minus minus. Right? Minus minus. So that means both of these are going to be multiplied, right? It's going to be underneath here, and this is going to be right next to it. So what I'm saying is, if we rewrite this, this is going to be log x cubed, right? Because the power can come up, plus log, all right, 4 is the argument, and underneath it, x times 6. Okay. 4 and 6 can be reduced to 2/3. And then, because it's addition, we can multiply the arguments. So combining 2 logs into 1 log, we're going to get log. And the argument's going to be, so we have a 2 x cubed over 3x. So I have 3 x's up top, 1 x in the bottom. So that's going to cancel. This is going to cancel, leaving behind x squared, right? Because there's 3 x's up top, essentially x times x times x. And then you can cancel that. So final answer, log 2x squared over 3. So here, when you have the minus minus, just dealing with logs so much, when you're expanding them, I know that when you're doing this, it's going to be log 4 minus log x6. And then, like, I'm just making up things here. This is going to be, that negative has to distribute, essentially. Right, so I'm already, like, keeping that in mind. That, like, I'm, like, thinking ahead. So hopefully you can too. Okay, 37 looks like a mess, but it's actually not bad. So all this is addition. So they're going to be multiplied, except for this one, right? This argument is going to go underneath, and then everything else is going to get multiplied up top. So the first rewrite step, natural log x plus 1 cubed, right? Because the power can come up. Okay. Over y squared. Again, the power can come up. So this is going to be all inside the argument, right? Plus ln y plus ln 2. So anytime you see that minus sign when you're condensing, just know that it goes underneath, the argument goes underneath whatever is the argument to the left of it. So now, because it's addition, everything gets multiplied basically up top. So here's one thing I don't like that I did. Natural log x plus 1 cubed over y squared. This I like this better, right? Because this is the argument. The other way it looked like the cube could be applied to the y squared in the bottom. That's not true. Okay, this is better. Plus natural log y plus natural log 2. Okay, then rewriting this, combining this as 1 log, natural log, right? It's all 1. And up top is going to be 2y, right? Multiplying x plus 1 cubed over y squared. And then, right, there's a y on top and a y on the bottom. So that's going to cancel. So final answer, natural log 2 x plus 1 cubed over y. Final answer. Okay, number 38, without a calculator. All right, so these are actually fun in my opinion. All right, so they tell us log base 3 of 4 is equal to this number, approximately. Log base 3 of 7 is equal to this number, approximately. Okay, so I'm going to rewrite log base 328, number 38. And somehow logs 4 and log 7. So can I make 28 out of 4 and 7? That's the question. So this is log base 3, 4 times 7. It's 4 times 7, 28. Yes, it is. Okay, so now, because it's multiplication, we can rewrite this as log base 3, 4, plus log base 3, 7. And we replace each of those with the given information, right? This is 1.262 plus 1.771. Add these together, lining up the decimals. 3.033. So I have to remember those numbers. Here, not 39, subtraction. Log base 3, 7 minus log base 3, 4. So 1.771 minus 1.262. Again, lining up the decimals. 0.509, right? Basic subtraction. Hopefully I did that correctly. All right, log base 3, 16, so number 40. So 16. Can I make 16 out of a 4 and a 7? I can. This is going to be 4 times 4, or 4 squared, right? However you want to look at this. Log base 3, 4 squared. Power and come down. So this is going to be 2 times log base 3 of 4, which is 2 times 1.262. So 2.524. 41. Base 3 is 49. 49 is not divisible by 3. So we can do, but to make it a 4 or 7, right? Using 4 or 7. So this is basically like the last problem, but just with the 7. So this is going to be log base 3, 7 squared. 2 can come down because of logarithm properties. So 2 times log base 3, 7, which is 1.771. 2 times 1.771. So multiplying this out, 3.542. 3.542. Okay, 42. Log base 3 of 1/4. So subtraction. So log base 3 of 1 minus log base 3 of 4. So log 1, right, this is just going to be 0. So we have 0 minus, so you can see it, 0 minus whatever log base 3 4 was, 1.262. Yeah. Or 1.262. So negative, so 0 minus that, negative 1.262. All right, 43. 43 looks fun. So this is going to be log base 3. So 49 is 7 squared. 64 is 4 cubed. 4 cubed. 4 times 4 is 16. Times 4 is 64. Yep. All right. Division, subtraction. So log base 3, 7 squared, minus log base 3, 4 cubed. Powers can come down. So 2 times log base 3, 7, minus 3, log base 3, 4. So substituting in the appropriate or the respective values. 2 times 1.771 minus 3 times 1.262. Okay, without a calculator, we gotta do this. So 2 times 1.771. I feel like we did that already. Yeah, 3.542 right here. So work smarter. 3.542 minus, did I do it at 3 times that yet? No, but that's fine. So 3 times 2 is 6. 3 times 6 is 18. Carry the 1. 6 plus 1 is 7. 3. So subtract these. Definitely going to be negative, right? Because we have a small number minus a big number. It's definitely going to be negative. So 3.542. You may be saying, hey, you're doing it the wrong way. Well, yeah, but I know that's going to be negative, so it doesn't even matter. So 4, 0.240. So negative 0.244. Gotta be nice at subtraction. All right. Change of base and a calculator. Use change of base and a calculator. Okay, so I'm just gonna do the change of base part. You can do the calculator part if you want. But so this is easy. So let's just review it real quick. What change of base is? Change of base, right? What that mean? It means that you have a log base whatever to whatever argument, log base b to a, right? If you have this, then you can rewrite it as a fraction with some new base of your choosing. The a goes up, log same base in the bottom, and the b goes down. So the way I remember it, this number goes up, this number goes down, and I can use whatever base I want. Right, the argument goes up and the base goes down, and you can use whatever argument you want. Me personally, I like natural log, right? So what I'm saying is the 12 is going to be natural log 12, the 7 is going to be natural log 7, and then you basically put them over one another. So a faster way of doing this is, so when you have change of base, you have one log, you're going to end up with two logs, right? You're going to split it up into two logs. The argument goes up and the base goes down. So natural log 12 over natural log 7. Throw in the calculator and see what happens. All of these are going to be like that, right? This is going to be natural log 112 over natural log 4. You could use whatever base you want. I like base E just because natural log is so much easier to use. Natural log 18.1 over natural log 4.2, right? Just remember that the way I remember it, the base is a little bit lower, so that's the one that goes down, and then the argument goes up. Okay, and then they always try to hit you with something to trip you up, but never fear. Stick to the script. So the argument is this over this, and then put it in the calculator. Put it in a calculator. I have my calculator here. You want to see it? All right. Convinced me. So controlled division brings up a little symbol that looks like this. Control E makes ln 12 over ln 7. So approximately 1.28. Yo. All right, number 45. ln 112 over ln 4. So I up arrow twice, highlight the last one, and then just replace the information. Or actually, I'm going to add a 1 because it's 112. So approximately 3.40. Oh, the last one was 28. My bad. All right. Up, enter. (18.1) over 4.2. Natural log, that is. All right. 2.02. Approximately 2.02. Negative 0.53. All right, number 48. We first check to see if we can write them as the same base. So 7, 3x plus 4 is equal to 7 squared, right? Because 49 is 7 squared. 2x plus 1. Power raised to a power, you multiply. So this is going to have to distribute. So 3x plus 4 is equal to 4x plus 2. The bases match, so we can equate the exponents. So minus 3x, minus 3x, minus 2, minus 2. So x is equal to 2. Number 49. Using 3, we can use 3, base 3. So 3 squared. This will be 3 cubed. And we distribute. So 3, 12x minus 3, 3, 6x plus 16. Set the powers equal to one another. So x is equal to 19/6. Okay. This can be rewritten as 10 squared in the denominator, which can be rewritten as 10 to the negative 2. Distribute. Set the powers equal to each other. So x is equal to, this is divisible by 3. 4/5. 4/5. Okay. Logs now. So log on the left, log on the right. Arguments must equal, must match. So x plus 19 is equal to 7x minus 8. So x is equal to 3 goes into 27, 9. 3 goes into 6 twice. So x is equal to 9/2. When we're doing logs, we always want to check and see if this will work. Well, what I mean is, whatever we think x is, we have to plug x back in and make sure that the whole argument is positive. So 9/2 plus 19, that's going to be a positive number, so I'm not worried about that. The subtraction one, though, however. So 7 times 9/2 minus 8. So this is going to be 9 times 7. Well, 9/2 is bigger than 1. So that means it's going to be a really big positive number. So 63 over 2. So it's like 30 something. 30 something minus 8 is still a positive number. So yes, this works. Right? Anytime you figure out what x is, you always want to take x, put it back into the log, and make sure that the whole argument is positive. Like, we don't care what it is, just as long as it's not 0 and it's bigger than 0, right? It has to be a positive number at the end of the day. That's what it means to be positive, greater than 0. Anything greater than 0. If it's 0 or less, then it's no solution. So here, log on the left, log on the right, same base. So the arguments have to equal each other. Okay. So here, x is equal to, what is this? 14 over 4, 7 over 2. 7/2. All right, so let's check and see. So 3 times 7 over 2 minus 10. This is going to be 21 over 2 minus 10. It's 21 over 2. 11.5. 10.5. 10.5. Is that true? 20.5. Yeah, okay. So minus 10, this will give us a positive 0.5. So in the first log, we're good. Second log, 14 minus 5x. So 14 minus 5, 7 over 2. It's 35 over 2. Half of 35. So half of 36 is 18. So 17. 17.5. Right, that's 17.5. Right, because that's 34 plus 1. So 34.5. So 14 minus 34.5. Right, I don't care what that is. I just know that it's negative. I know that it's going to be negative. So no solution. I don't even have to calculate it. It's going to be negative. Right. 7/2 worked in the first one, but it didn't in the second. So, couldn't even see it. 14 minus 34.5, which is a negative number. No solution. All right, 53. Okay, we only have a log on the left, so this one's slightly different. The power is going to come up. So log base 2 x minus 4 squared is equal to 12. So I got the log as condensed as possible, right? Not expanded. Expanded, the power comes down. When you condense, the power goes up. So the reason I'm condensing it is because I want to rewrite it as an exponential, right? 2 raised to the 12th power should equal this over here. So 2 to the 12th power is equal to x minus 4 squared. Okay, 2 to the 12th power. They say we get a calculator. Nope, no calculator. All right, of course. Well, all right, so 2 times 2 is 4, times 2 is 8, times 2 is 16, 32, 64, 128, 256. 256 times 2, 512. 512 times 2, 1024. All right, so let's write that down. That's to the 10th power. All right, times 2 is going to be 2048. It's a fun game, by the way. So it's the 11th power. Times 2 would be 40, 96. Okay, so what is this saying? This is saying that 40, 96 is equal to x minus 4 squared. So it's a binomial. So x times x is x squared. Negative 4 times negative 4 is positive 16. And then 2 times this times this. So negative 8x. Okay, this is horrible. But it's all right. I'm subtracting. So this is going to be 0 is equal to x squared minus 8x minus 40, 86, 40, 80. Okay. I figure out what x is. It's quadratic. Do I even stop to think what two numbers multiply to make 40, 80 that add up to 8? Just use the quadratic formula. So A, B, C. So minus B plus or minus B squared minus 4AC all over 2A. So get that out the way. I know what it is. All right, so minus B plus or minus negative 8 squared 4 times A times C all over 2A. So 8 plus or minus 64 plus 40, 80 times 4. 0. 4 times 8 is 32. Carry the 3, but all right, so x is equal to that. So let's think about that for a moment, right? Like, I mean, there's a positive version, then there's a negative version. Definitely not the negative version, right? Square root of 16,000 is going to be a positive number. If I add 8 to it, divided by 2, it's still going to be a positive number. And then I'm basically subtracting that, or 4 from that, right? Because I'm plugging it back in. So the positive one's going to work. The negative one's not going to work, I don't think, because 8 minus a very large number is still a negative number. Divided by 2 is still a negative number. So the negative one definitely won't work. Okay, 54 through 56. Solve algebraically. Calculator allowed, but no intersection allowed. Show work. Okay, so this is going to be very similar to 48 and 50, right? The only difference is here we had to get the same base. Here, we ain't getting the same base. Like, there's no base that you can make out of 8 and 20. The only way here, and they give us a calculator, so I can do anything I want to both sides. Right? This is crucial because that power comes down because that's a log property. Right? Take the natural log of both sides. Power comes down. Just so happens to be an x. That's what we want. Isolate x. And then it's calculator time. ln of 20 divided by ln of 8. Approximately 1.44. So let's try that again. Here, 55, the term with the x and the exponent is not by itself, right? So we make it by itself. So 2.1x is equal to 7 plus 5, which is 12. All right, I'm going to do ln to both sides. This is going to come down front. So 0.1x times ln 2 is equal to ln 12. Get x by itself. So 0.1 and ln 12, like I'm multiplying by ln 2, or ln 2, not ln 12, ln 2. So 0.1 times ln 2. So cancel. So this is equal to x, which is approximately, so straight to the calculator. So natural log of 12 over 0.1 times the natural log of 2. 35.85. It doesn't say, it says calculator allowed. All right. So exact answer and approximation. That's what it is. Okay. Same kind of idea. Got to get the x by itself. So minus 16 on both sides. Divide both sides by -3. So e to the 2x is equal to 11/3. It's in the variables in the exponent. So ln of both sides. Power comes down. So 2x times ln e. But ln e is just 1, so I don't care about that. ln of 11/3. Divide both sides by 2. So x is equal to that, which is approximately 0.65. Approximately 0.65. Okay, graphing. All right, so we're looking for 3 critical points. So the critical points are going to be 1, 0, b, 1, 1 over b, -1. B being the base. So if we can figure out these 3 points first, given the base, and then we apply the appropriate transformation. So 57, we have, it's going to be a shift inside lies. So left 3. All right, so if we plot the 3 critical points, so 1, 0, 2, 1, and 1 over 2, so 1/2, -1. So these are the 3 critical points. Now we apply the transformation. So we shift them to the left 3 units. And the vertical asymptote for this is going to be shifted as well. Okay. So the domain, the x values is always going to be from the vertical asymptote. So -3 all the way to infinity. I guess you could say x is greater than -3. And the range, all real numbers. Little hint, the range in all of these are going to be all real numbers, by the way. All right. So we're shifting down 4, right 2. So again, base 2. So starting with our parent function, we're going to shift these points down 4 and right 2. So 1, 2, 3, 4. Okay. Domain is going to be from the vertical asymptote to the right. So -2 to infinity, or x is bigger than -2. Range is all real numbers. All right, number 59. So this is similar. The only difference is this negative is going to reflect it across the x-axis. So we're going to go up 3 and then left 1 and then reflect across the x-axis. All right, so we'll do these one at a time. Again, base 2. So let's start with 0, 1. So 0, 1. We're going to go up 3, left 1, and whatever that is, we're going to reflect it across the x-axis. So we're going to go up 3, 1, 2, 3, to the left 1. So here, and we have to reflect this point across the x-axis. So that means it's going to, so we're 3 up, that means we're going to go 3 down. So I'll do it in blue. So this is the point we want. Okay. Here's 1/2 -1. So I'm going to go up 3 to the left 1, then reflect it. So 1, 2, 3, 1, and then we'll reflect that across. And then last we have 2, 1. So this is going to go up 3. So 1, 2, 3, left 1. So we're 4 up. So that means we're going to go 4 down. Vertical asymptote is going to be at -1. There it is. So the domain is going to be from -1 towards infinity, or x is just bigger than -1. So plot the critical points and then apply the appropriate transformation. All right, 60 to 64. This is going to be no calculator. Solve using logarithms, show your work. Okay, so this is basically compound stuff. So, all right, so let's look at this. What kind of compound are we doing? So you want $400 to double in 6 years. If the interest is compounded continuously, okay, so that means A is equal to P E R T, right? Continuous, compounded continuously. So I want $400 to double. So this is my initial to double. So 400 doubled would be 800. That's my A. 6 years is your T. What is the rate? So we're looking for R. So this is going to be 800 is equal to 400. E, R, T is 6. Okay. We just plugged in all the values. Getting the R term by itself, divide both sides by 400. 800 divided by 400 is 2. E, R6. ln2. Take ln of both sides because that's what's going to bring this down. So ln2 is equal to R times 6. Right, ln E just cancels anytime ln and E are next to each other. Divide both sides by 6. So ln2 over 6. Oh, do not use intersection, but we can use a calculator. Okay, that makes sense. I was like, how am I supposed to figure out what this rate is? So on a calculator, let's do ln2, and then that's going to be divided by 6. So it comes out to approximately 0.16. Let's round a little bit further. 1155. So 0.1155, which is basically 11.55%. So the rate would be 0.1155 or 11.55%, how you want to look at it. All right, 61. Suppose $600 is invested. So words mean things. So this is the amount we're investing. So my initial amount. My rate, which is basically 0.06 because you have to turn percents into decimals for this to work. Compounded continuously, there's that word again. When will the investment be worth $1,800? So this is going to be your future amount. So 1,800 is equal to 600. E 0.06 T, because it says how long, right? Or when. When is T? That we don't know. All right, divide both sides by 600. So 18 divided by 6 is 3. Take ln of both sides. So ln3 is equal to 0.606 times T. The ln E went away, if you're wondering. Okay, T is equal to ln 3.606. So put that in a calculator. ln 3.06. So 18.3 years. 18.3 years. All right, an iodine solution has a half-life of 45 days. Find the constant K. So this type of problem, it's basically the same thing. Some future value equals the initial value, which is N instead of P, EKT. So a PERT is strictly money. But in general, whenever we are figuring anything else, typically chemicals and bacteria, we use this form where K is a constant, like the rate. Okay, determine the number of days it will take 35 grams. So this is your N value to decrease to 7 grams. So 7, 35, K, T. This is what we're looking for. So the first thing we need to do, because we have two variables, so the first thing we need to do is find K. So we need to use K, or find K, with the first sentence. So it's a half-life of 45 days. So that means whatever number I have in 45 days, I'm going to have half that. So we start with whatever number we want. I'm going to start with 1. So if I have 1 initially, and then 0.5, because that's what half is, that's what I'm going to end up with 45 days later. So E, K, 45. So half-life, you choose someone, like, right, even if I chose, like, say I chose 2, then if I chose 2, what's half of 2? 1. Okay, you're like, oh, well, you don't want decimals. Okay, yeah, but I'm going to have to divide both sides by 2, and this is going to cancel. I'm going to get 1/2 on the left anyway. So if we use 1 and 0.5, that's what I'm saying, right? So, and it doesn't matter what number you use, you're going to have to divide by that, and because you chose half, it's always going to come out to 0.5. So deal with it, right? So this is going to be ln on both sides. So ln of 0.5 is equal to K 45. Right, because ln E is going to go away. Divide both sides by 45. To the calculator for K. So ln 0.5 over 45. So this is negative. So K is going to be negative 0.0154. All right, so we have our K value. So let's take that K, plug it here, because that's the rate. And we're decreasing, so it's negative, so it's all good. So 7, 35. Oh, look, there should be an E right here. E, K, negative 0.0154, T. So divide both sides by 35. So 1 over 5, 0.2, right, that's equivalent to 0.2, 1/5, is equal to E negative 0.0154 T. Okay, so here I'm going to take ln of both sides. So ln of 0.2 is equal to, ln E cancels, negative 0.0154 T. Divide both sides by that figure. T is equal to 104. 104 what? Right. Days. They said days. So 0.5 days. 104.5 days. 104 and a half days. Okay. Same problem. Or 63. Similar problem. So K is this. T is measured in days. So we don't know what days is. How long? So that's what we're looking for, right? To take 30 bacteria and increase to 2400. So 2400 is equal to 30. That's our initial. E 0.825 T. All right, this is very basic. So we're solving for T. So 240 divided by 3, 80. Okay, ln on both sides. Right, that ln on both sides thing is it's pretty crucial. Like it's very useful for sure. So 5.3 days. Okay. What do we have here? What is this asking? So North Valley School District has had an increase in student population from 1999 to 2005. The enrollment in 1999 was 5,000. Okay. Each year for 6 years, the enrollment increased by 4%. What was the total enrollment of? Okay, check it. So we started out in 1999, it was 5,000. All right. Every year, it increased by 4%. So that means 1.04, right? Because 4% is really 0.04. And I need that to be bigger than 1 for this to increase. Right? Because let's just say I didn't. And I just used 1. Okay, well, 5,000 times 1 is just 5,000. Like there was no increase. Right? No matter how many years I do it, 1 to the 6th power is just 1 times 5,000 is 5,000. So there was no increase. So it has to be bigger than 1 for it to be an increase. And then it says following the same pattern. Okay, so first off, let's figure out what this is. So now that we have our formula, we go to the calculator. 5,000 times 1.04 to the 6th power. So in 2005, we had approximately 6,327. If we follow the same pattern, how long will it take the district to double its population? So we want to know same problem. How long? So X is the year to double. So 10,000. Divide both sides by 5,000. So 2. Right? ln on both sides. So this is going to be X in front times ln 104 ln 2. Divide both sides by ln 104. And we get 17.6 years. If it follows this same pattern, 17.6 years. So like, what was that 2016? 2016, it should double. All right. Good luck.